Okay, so hello everyone. So welcome to attend our this week Rutgers Efficient AI seminar. And today we're very glad to have the Professor Hyoukjun Kwon from the University of California, Irvine to give us this talk about the ML workload to the in AI and VR and their implication to the ML system design. And Professor Kwon is currently assistant professor in EECS department at the University of California, Irvine. And his primary research area is computer architecture, and his research focus on AI accelerator, hardware, software co-design for emerging workloads such as augmented and virtual reality. He was a research scientist at the Meta Reality Lab before joining the UCI, and he received his PhD in computer science at Georgia Tech in 2020. And his research works have been recognized by IEEE topics in computer architecture conferences for twice, and honorable mention at the IEEE ACM Single Arc IEEE CS TCC Outstanding Dissertation Award. And so now let's welcome Professor Kwon to give this talk.
Okay. Yeah, thank you very much for a great introduction, and thank you for having me today in this seminar. I'm really pleased to talk about my recent research related to the ML workload in AR/VR systems and their implication to the system design. So before I talk about the main technical contents, I wanted to briefly talk about the mainstream consumer computing platforms and how they evolved over time. So I will not go all the way back to the ENIAC era, but let me start from the desktop. So in the desktop era, so the computing was available at fixed location, and we interfaced the computer using keyboard and mouse. And when we entered the mobile era, the computing is moved to any place when the user holds the device in hand. And interface also evolved into touchscreen, so we don't need keyboard and mouse anymore. Then we can interact with the computer system, using our fingers. This was a big innovation. And now we are heading to the next generation of the computing platform, which is wearable. When we have those kind of wearable devices such as augmented reality, the glasses, the computing is now available any place, anytime, whenever the user is wearing that device. And interface will also evolve. So we have more natural way to interact with the computing platform, such as hand gesture or hand location and eye gaze and speech and so on, just as if you are talking to other people. So here are several important aspects. So any place, anytime, which means the device need to understand the context. For example, if you are in the lecture room, but the device suddenly tells you, okay, there's a great the video game streaming, so I will turn it on for you automatically, then that's a problematic. So the devices also need to understand the context of the user. And because we will have more advanced interface, like more natural way to interact with the computing platforms, we need to process multimodality inputs. So the speech and the hand gesture is good examples. For for processing speech, we need uh, the mic input and the corresponding software and hardware to process that. At the same time, we also have camera inputs for the hand gesture. So we also need to process that modality. So basically, we have multiple modalities, and we need proper processing software for those multimodality inputs. And current trend in the wearable devices is enabling all of those features using ML, machine learning. So my talk will first talk about the machine learning workload in AR/VR. And then I will move on to the hardware system design using one of our recent work as an example. And then I will discuss how should we design software system, and then I'll conclude my talk. So let me begin with the workload side. First of all, I wanted to acknowledge these amazing colleagues. So this work was based on this collaboration, and yeah. So for the workload parts, I will talk about the new class of the machine learning workload, which is we named as real-time multitask multimodal.
我也要那
Sorry, was it a question?
I think there's some noise. Yeah.
Oh, I see. Yeah. Okay, so that's the new class we identified, and I will discuss characteristics and challenges, and I will briefly introduce the XR bench, the new benchmark in of those new class of the ML workload, and I'll discuss scoring metric, and I will discuss case studies results. So let me begin with the new class of ML workload. So we have ML models everywhere today. So in smartphone, so the typical services include translation and photo denoising and so on. And in self-driving system, for example, there are many the sub-tasks that relies on AI or ML, such as lane detection, vision-based navigation, and data center. We all know that we are running every sort of machine learning workloads on data centers. So current trend is you are using multiple ML models for diverse small tasks within a complex task. So let's think about the overall workload in the axis of the model concurrency and intermodal dependency. So let me begin with the simple example on the ML Perf-like workload. So at the beginning of the ML, we just ran single task on a single model, and we were okay with just looking at the image classification result or image object detection result. So in that era, we didn't have model concurrency. We just ran single model, and because we just ran single models, there were no intermodal dependency as well. And we moved on to the multi-tenancy era. So in the data center, we ran a lot of single model inference workloads, which include recommendation, chatbot, and video analysis. There were many applications. But in the early era, there were no complex intermodal interaction. So we just used single model for single task. But this is an interesting example. So when you have a smart speaker, and you usually smart speaker has support the speech-based interaction, and they require some wake words such as "hey something" or "hello something," then the speaker will wake up and wait for your speech input. Usually, those are all implemented by the ML model. So keyword detection is for catching the wake words, and speech recognition to understand what user says after that. So if you take a look at this example, we now have two models, multiple models. And interestingly, they are connected in a dependency. So, and only if the keyword detection result is positive, we will run speech recognition. So this is a great example where the intermodal dependency exists, but they are not run in concurrent manner. Now we are moving to more complex workload, which we named as multitask, multimodal ML workloads. So examples include the augmented and virtual reality and autonomous driving. So we will have multiple of this kind of machine learning model pipeline running in concurrent manner. And this is a new trend in the ML workload. And this is what exactly we will focus on during this talk. Then what are so new about this new class of workloads? First of all, we have both concurrent and cascade models. And these kind of applications often require real-time processing. And these workloads are often tightly coupled with the sensor and the output device. So we need to consider full system level pipeline. And those applications rely on multimodality input sensor inputs. And the workload itself will need to change based on the user input. So for example, in the AR VR, to the VR headset, if you don't have any hands in the scene in front of you, then the headset doesn't have to run the hand gesture recognition or other downstream tasks. So this is a quick example of this. And as I mentioned at the beginning, so this kind of workload need to be context aware around the user. Then what are their implication to ML system design? So these are certainly a new characteristic but these are just examples. So there are many implications, but I'm just focusing on one example per each characteristics. For concurrent and cascade models, we need to consider them when we schedule ML model inferences. For example, we cannot schedule a downstream model before the upstream model has completed. For real-time processing, we because of this real time, we need to consider many real-time system aspects such as deadlines. So when you optimize the system, you need to optimize for the deadline, not only for the latency, because removing latency beyond the deadline would not be very helpful in the real-time system. And for the full system pipeline or SOC level pipeline, when you schedule the workload, you need to be aware of the input sensor and output device. For example, the output display may have the refresh rate, and if you are giving outputs in a different rate than the refresh rate, it will be a little bit so there will be some challenges around there. So those need to be considered when you schedule workloads. And for multi-model inputs and models, because we have multimodality speech, the gravity sensor and the camera and so on, so the ML models processing those modality becomes heterogeneous. So these need to be incorporated in the hardware design. And context-driven workloads, basically you get highly diverse workload depending on user context. And user input-driven dynamicity, so you need a very good runtime software support for processing the user input quickly. As we saw by these examples, there are many, many implications arise from these new characteristics from this new class of ML workloads. So to drive the system design, so we need to better understand the workload itself. That's why we work on a benchmark that can be representative of this new class of ML workload. And the name of the benchmark is XR bench, focusing on the XR or cross the augmented XR basically means both augmented and virtual reality. So let me first discuss the uni models, ML models included in the XR bench. So there are three key task classes and uni models in XR bench. The first class is user-device interaction. For speech-based interactions, as I showed in one of the previous examples, there's a keyword detection model that captures the wake words and connected to the speech recognition model. And for enabling hand-based interaction, we need a hand tracking model. And to enable eye-based interaction, so you have the eye tracking pipeline. So in XR Bench, we adopted a previous work that utilize eye segmentation followed by gaze estimation. And the second class is user context understanding. For vision-based context understanding, so there are semantic segmentation, object detection, and action segmentation models included. And for audio-based context understanding, we have keyword detection and speech recognition, just like these models. And word locking. So this word may not be very familiar for many people, but this basically means how can we identify how to draw AR augmented reality object on the real world scenes. So for example, we can use plane detection to identify where to draw the planar AR object in the scene. And we also need depth estimation to identify the proper size of AR object to be drawn in the user scene. And this is a quick note about all of these workloads. So there are many, many emerging workloads as well. So this covers a subset of AR/VR workloads. And we are working hard to update this benchmark to reflect the latest advance of those the ML model use cases. And combining those unit models, so we constructed usage scenarios which is more aligned with real use cases projected by industry. So for example, this is a social interaction B scenario in XR Bench. So this is targeting some application like action-based AR emoji drawing during in-person conversation. To enable this application, first, the device needs to understand where user is looking at. So that's why we need eye pipeline. And we also need action segmentation to understand the opponent's action so that we can draw proper AR emoji. And one several things we can immediately notice from this workload description is that two models have dependency in some cases, like iPipeline, and we are running these ML models and ML pipelines concurrently. And because this is a real-time processing, there are FPS or frame per second requirements associated with each model. And benchmark is built in this way. So we are providing the unit models and which model we need to run concurrently and what the target FPS. So to briefly provide the high-level overview XR bench, these are the unit models I discussed, and I'll not go into all the details, but as you can see, the models are listed and associated data sets were listed, and there are also accuracy requirements. And when we selected those models, we considered the workload to be aligned as much as possible with the industry use cases, and we considered model efficiency because it needs to run on the wearable devices or nearby mobile devices. And we also focus on model performance. We want to include good models, not outdated models. And the user scenarios, as I mentioned in the previous slide, is a better reflection of the real applications projected by industry. And depending on the usage scenarios, some models are utilized, some models are not utilized, depending on the user application. And we provide the FPS goals for each model within each usage scenario, as you can see in this table. And for details, so please refer to our papers. And I'll move on to the scoring metric. So one thing we learned during our case studies was that the traditional metric itself doesn't work really well on this kind of new workloads. So I will get to that point when I discuss the case studies. But that was the motivation for us to take a look at the new metric for evaluating ML systems for this kind of new workloads. So our approach was defining 4 unit scores, focusing on the 4 very important aspects of those systems. The first unit score is real-time score. It measures the degree of deadline violations. So please note that we are not evaluating absolute latency, but we care more about deadline violations because it's a real-time system. And we also care about energy because of wearable devices, so the battery will be the prime challenge. And accuracy, which is actually the model performance. So we want to get high quality outputs from each model. And quality of experience is also important metric. So there are many ways to define this metric, but in this work, we define it from the frame drop rate. For the real-time score, this is a very high-level overview of how the real-time score changes. So x-axis we have latency and y-axis we have the real-time score, and we designed this score to be 1 all the time near the deadline. But when it get closer to the deadline, when the latency gets close to the deadline, it's sharply drops around the deadline. And if the deadline is violated, then the real-time score becomes 0. So we formulated in this way. And just like this score, everything is formulated between the 0, 1 range, and we formulated everything in the higher is better metric. The primary reason for those is because we want to combine those scores to construct one comprehensive score. So the left side figure shows the overview of those metric formulation, but I'm not going to all the technical details, but let me just highlight some high-level features. So those scores were formulated in hierarchical manner. So we define the scores from fine grain to coarse grain units. So for example, for each inference runs, and for each reinforcement run for each model, we can define scores. For one model, across all the inferences that happen the given time frame, we can also define this score. And then for all the models, including the usage scenario, and for the given time window, we can also define these four scores. So, and for entire usage scenario, we can also define scores, all of those four scores, and we provide some hierarchical formulation to compute that from the fine-grained aspect to the coarse-grained aspect. And those scores are composable. So each unit score is ranged to be 0.1. And by multiplying them, as you can see in the topmost box in the left side figure, the basic idea is multiplying them together to get a new comprehensive score within 0.1 range. But why is a single metric useful? Because comparing one number is definitely easier when you optimize the system. And some the companies are hesitant to share some details about each unit score. Then we can just request them to share one score. Then I think it'll also facilitate the participation from industry. So those are two primary reasons. But the benchmark harness itself will still report the unit score so that the users can focus on what they need. And yeah, there are kind of formal definition of all those score metrics, but I will not go into all the details again. And if you're interested, please refer to our paper. And I wanted to discuss some interesting case study results. So we focused on these key questions in this case study. So why do we need different usage scenarios? And why do we need new benchmark score? And what are the new implications to the ML hardware design? And for these case studies, we focused on the ML accelerator systems. So we had two accelerator sites. So those with 4K PEs and 8K compute units or PEs. And we evaluated various accelerator architecture styles. The first style is fixed data flow, which is a traditional style. And SFDA just means multiple FDA, the fixed data flow accelerator instances within a single chip. And the third category is heterogeneous multi-instance accelerators within a single chip. So in short, it covers many possible variant architectures in the ML accelerator system. And we examined all of those options using our XR bench. So these are the full result presented in our paper. So, but I will not go into all the details. So let me just highlight some interesting results. But before I go into some more details regarding one usage scenario, so from the high-level glance, we can easily see the scores are pretty much different depending on the usage scenarios. So this is one high-level evidence that we need different usage scenarios that covers the many of those actual use cases of the AR/VR devices. But let's take a look at a more detailed look of one result on the AR gaming usage scenario. So x-axis, we have the accelerator styles listed as from A to M, and the left side figure is for the 4K PE system, and right side figure is 8K PE system, so larger accelerator. And y-axis, we have scores defined, the XR bench scores, basically what we defined, so between 0.1. And if you take a look at this part, we can see the real-time score is 0, and that made the overall average score 0 because basically the basic formulation is cross product of all the unit scores. So in this case, we see very high QoE score, which means the frame drop rate was very low, and energy efficiency was also quite good. However, it got 0 real-time score, which the implication to the user is actually the significant output lag visible to users. This basically means there are significant deadline violation for each frame. So the XR bench comprehensive score became 0 as well. So although energy efficiency and the QA itself is good, but this is a big problem for the user. So in short, we need to consider all the aspects when you evaluate ML systems for this kind of workloads. So we need to thoroughly consider those all the key requirements. That's why we need those diverse unit scores to capture all of them. And let's take a look at this. So with these results, we try to answer what are the new implications to the ML system design. So on the x-axis, this is a time, and y-axis, we have two different accelerator instances within a single chip. And these are on this tiled accelerator, so heterogeneous data flow accelerator, which runs wave stationary and opposite stationary data flow each. And you can view this, the black square is a one chip, and within the chip, we have two accelerators included, and we are running some models in concurrently. For the first case, we can see, so this is basically a timeline. So if there's no the white gap, that means we overutilized all the accelerators very well. So utilization was almost 100% for this case. However, if we take a look at QoE score, we identified it actually involved 47% frame drop. For the second case with AKPEs, we can see some white space over here, which means the utilization was not 100%. So we observed around 90% utilization, but we saw only 3% frame drop overall. Then the question is, which system is better, right? In hardware design, we often use the utilization as the optimization metric, but if we only care about utilization for this kind of application, actually we miss a lot of important aspects such as frame drops. If almost half of the frame is dropped, then we cannot call that a good system. So this is one interesting case that the traditional metric itself doesn't work really well on this kind of workloads. So we do need to consider all the aspects together when we design a system for this type of workloads. And this is just one example case study, so there are more included in the paper, so please refer to the paper if you're interested. And for the overall, the result we observed, so we found that heterogeneous multi-accelerator systems or heterogeneous data flow accelerator systems outperformed other accelerator styles. So that's why I will present a little bit more detail regarding the heterogeneous multi-instance accelerator system or heterogeneous data flow accelerator system. So what is the heterogeneous data flow accelerator? So the left side figure illustrates the high-level idea. So within a single chip, you could have multiple accelerator instances, so which we call as sub-accelerator. So each of them can have different number of PEs or compute units. They can have different buffer size. In addition, they can support different functionality by having different specialized unit, and they would have different interconnection that enables different data flow style. The main idea is deploying multiple of the very highly specialized accelerators, which are different. And when you run as a model, we cherry pick the best accelerator for the given model or layer. So this architecture considers the concurrent cascade models and multimodality input in mind. For concurrent cascade models, if you have three concurrent models, very high level intuition is you could run each model in each sub-accelerator instances. So this is good for model concurrency, model parallelism, and for multimodality inputs, we basically have heterogeneous workloads. And if you have heterogeneous backend, then it's more likely that you can match the more appropriate sub-accelerator with the incoming workload. So those are high-level ideas regarding this. Then let me discuss why HDA. So why heterogeneous data flow accelerator? So benefits, as I briefly discussed, it provides some flexibility in data flow. What does it mean by that? So this is related to the point I mentioned when I discussed the heterogeneity of the workload. So by having different styled accelerators, we can cherry pick the most preferred sub-accelerator for each layer. So this is very good characteristic for the multi-model inputs and models, which is one of the characteristics of the MTMM workloads. And this has low hardware costs compared to the fully reconfigurable data flow accelerators because it has simpler hardware than the reconfigurable data flow accelerators. And it naturally supports model parallelism. We can parallelize layers in different models across sub-accelerators and run different models concurrently. And this is preferable for multimodal workloads like AR/VR I mentioned at the beginning. But there are also challenges, as you can imagine. So we need to split the finite hardware resources across sub-accelerators, and each sub-accelerator is less powerful than a just big reconfigurable data flow accelerator. And each sub-accelerator instances need to share global resources, such as the global buffer, and the on-off-chip bandwidth. This can delay layer execution, and this could limit the model parallelism. And even if we have this many accelerator instances, we need to run layers in a dependency order. For example, if you have just single model workload, you cannot exploit the layer parallelism because of this dependency. So this also can delay the layer execution and limit the model parallelism. So actually, these challenges also give interesting optimization problems. So first challenge is related to the hardware resource distribution optimization. And the last two are associated with the layer execution scheduling problem. And we found these problems are very important for heterogeneous data flow accelerators. For the hardware resource distribution in our evaluations, we found 17% EDP. And the second optimization problem, layer execution schedule, has impact of 24% EDP, which is also quite significant. So the implication of these results is that the heterogeneous data flow accelerators need to be carefully optimized. And hardware and software, the second problem is more about the software side, so those need to be co-designed. And that's why we developed an optimization framework. And using the framework, we can we optimize the accelerator, and this is the result we got from the XR bench. And the highlight box here is the result for the heterogeneous data flow accelerators. And yeah, this is again the x-axis we have different accelerator styles, and y-axis we have the XR bench score. And in the red box is the result for the heterogeneous data flow accelerators. And in our evaluation, we found the four-way HDA, which includes the four sub-accelerators, provided the best score on average because it's well suited for the concurrent execution of multiple models, and it has heterogeneous data flow that is more aligned with the heterogeneous workload for different modalities. So that was the hardware part, and let me also briefly discuss the software aspect in terms of the scheduling. So this is again the characteristics of the new class of the ML workload I mentioned, so RTMM, real-time, multimodal, and multitask. What's their implication to the scheduling? So cascade models is basically the implication, basically dependency across the model, and concurrent execution of ML pipelines. So the scheduling, we need to be a little bit careful of the starvation of the specific ML pipeline or ML model. And this is a real-time application, so we need to meet the deadlines driven by the target FPS and device form factor. So these kind of workloads are often targeting embedded and wearable devices, so we need to consider energy as a prime optimization target. And user input-driven dynamicity, so and the context-driven workloads, their implication is basically dynamic behaviors in the workload. And we found those dynamic behaviors are one of those key aspects. Not only the first four, but dynamic behaviors are also a key aspect we need to consider for scheduling. Then, how does the dynamic behavior look like? We can categorize the dynamic behavior into three different categories based on their granularity. Task level. When a user is playing AR game, but suddenly receive the incoming AR call, then the entire workload usage scenario itself need to be switched to the AR calling. So this is an example of application change. In the model level, we can have some control flow in an ML pipeline. For example, you can implement the base interaction pipeline using hand detection model followed by hand tracking. If no hand was detected in a scene by the hand detection model, then we don't have to launch hand tracking. So this is one good example of the control flow in the ML pipeline in the model level. In operator level or layer level, there are many optimizations has been introduced in this domain. So this is just one example of the other previous work from other group. So this is a supernet switching. So depending on the system load, if the system load is light, then we can use the medium subnet or the larger subnet to deliver higher quality output. But the system load is high, then we can switch to the lighter version. That sacrifices the output quality a little bit, but it's much lightweighted, which is helpful for the heavy loaded system. Like this example, there are many optimizations have been introduced in the operator level. So those are examples of those dynamic behaviors in the RTMM, MTMM, the new class of ML workload I introduced. But the question is, how significant is it? So how important is it to consider them? In our evaluation, we observed about 32% impact on the deadline violation by considering and not considering those dynamic behaviors. So it is very important. So there are many considerations we need to keep in our mind for designing a scheduler. Then how can you design a scheduler in considering all of them? So our approach is pretty much similar as the XR bench's the scoring metric. So we define 4 unit scores for 4 important aspects. So first score is urgency. So how tight is the deadline based on the current status? And preference score, which accelerator is faster for each operator? For example, one layer could be faster on GPU or faster on NPU. Then if it's faster on NPU, then you may run on NPU, not on GPU. So this is a very high level description of this idea. And starvation score. So how long has each ML pipeline or each ML model has been waiting to be scheduled? So this is also one aspect we need to consider because we have concurrent execution and real-time processing. And energy score. So what is the expected energy consumption? Just like XR bench metrics, we all formulate everything within 0.1 range, and everything is formulated higher is better score to make it easier to be combined. And we thoroughly consider new requirements for this new class of ML workload, except for dynamic behavior until this point. But then how should they incorporate the dynamic behavior upon this formulation? So we introduce the comprehensive score utilizing these 4 unit scores, and we combine them in this manner. And we introduce extra parameter alpha and beta here. And these are the runtime tunable parameter for adaptivity for handling the dynamic behavior. And to quickly go over each term in this map score, so the first row is for capturing the real-time requirements, and the second row is capturing the requirement from the concurrency, and the third row is capturing the energy requirement. So in short, this formulation of the map score captures all the key aspects of the MTMM requirements. And those formulation good, but how do we tune this adaptivity parameters for dynamic behaviors? Our approach is focusing on the major RTMM metrics. So we utilize deadline violation, energy consumption. And as I briefly mentioned, the deadline violation, we need to focus on deadline violation, not latency, because it's real-time workloads. So latency reduction beyond the certain deadline doesn't really help. And we combine them into the EDP-like metric. which we define as UX cost, the deadline violation rate, and the energy. And the energy is normalized compared to the worst case energy profile before actually we run the workloads. And this is for keeping those each term within the 0,1 range so that we can also keep UX cost within the 0,1 range. And we use this metric profiled during the inference. So the high-level description of the parameter tuning algorithm for the alpha and beta, the adaptivity parameter, is setting sample points near the current values and find two sample points, minimizing UX cost, and compute the interpolation of those two sample points and move on to that point. And we don't focus on the single point that minimizes the UX cost because to prevent being stuck in the local optima. So that's why we interpolate two sample points. And this overall algorithm is inspired by gradient descent and simulated annealing. So I'm not presenting all the details of this algorithm, but let me just show how it works in the optimization space. The left side figure shows the UX cost, the heat map. So red means high UX cost and blue means small UX cost. So smaller is better. And x-axis has the alpha value and y-axis has beta value. And by changing the alpha and beta, we can get very different UX cost. Again, the UX cost is EDP-like metric. And if we run the optimization algorithm I mentioned, so it moves gradually to the optimal points, as you can see on the left side. So we found that our approach enables to get to the global minimum of the UX cost within 5 steps or less. And we tested this for the system boost scenario when the alpha and beta was the default value, and we want to find the optimal value after running ML models. And another scenario is the workload change scenarios. So this captures two interesting dynamic behavior scenario, and we validated this algorithm on those. So there are many results, but I'm not getting into all the details. So if you're interested, then please refer to our paper more details. And there are more optimizations. The RTMM, the workload characteristic aware optimization we introduced. One example is a smart frame drop. The main idea is let's make early frame drop decisions when deadline violation is definitely expected. The left side figure shows one example timeline. The x-axis is the time, y-axis is for each ML pipeline. By ML pipeline, I mean the cascaded ML models. And pipeline, phase pipeline are used in this example. And each box represents the latency for each model and for each frame. So F0 means frame 0 and F1 means frame 1. And let's assume that this is the current time. And we have the hand detection pipeline, a hand detection deadline here, and face detection pipeline here. If we run hand detection until the completion, hand detection, the deadline will be violated, and face detection deadline will be violated, and the second frame for the hand detection will be also violated. Deadline will be violated. So this is the expected result based on this. But if we make the early frame drop decision on the frame 1 of the hand detection, so we drop the frame here, then we can see the face detection for the next one is within the deadline, and hand detection from the next frame is also within the deadline. So compared to the 3 deadline violation versus 1 frame drop, so this can improve the overall system performance. So this is one example optimization we applied. And the main point of this optimization is we aim for the globally optimal schedule, considering all of those real-time requirements. And there are the many RTMM, the new class of ML workload aware considerations in this optimization technique. So we avoid dropping a model that has dependent models. sorry, excuse me. If you drop upstream model, then the downstream model also need to be dropped, and this will impact the over the output quality significantly. So we avoid dropping the upstream model. And concurrency, if we drop too many frames of the single model, then it will be also problematic. So we prevent starvation. And dynamicity, we also make dynamic decisions based on considering all the execution status and the change of the workload and so on. And this optimization improved 15% of the UX cost. Again, UX cost is EDP like metric. And based on all of these methodologies, so we just designed the scheduler. So I'll not go into details, but just highlight features. It enables fast dynamic scheduling. So leverages static and latency energy information. We can compute for the accelerators. There are many good tools such as time loop or Maestro and so on. And this scheduler provides adaptivity to dynamic behaviors. So it tunes the scheduling parameters, which are the alpha and beta I mentioned in the previous slide at runtime. And it includes many RTMM aware optimizations, such as smart frame drop. And it targets multi-accelerator backend, which is the heterogeneous data flow accelerator or multiple of the fixed data flow accelerator. And because we found the multi-instance accelerator system is well suited for the emerging ML workloads such as AR, VR. And in the evaluation for this scheduler, so we targeted two different styles of the multi-accelerator system. So homogeneous data flow multi-accelerator, heterogeneous data flow multi-accelerator, which means the homogeneous data flow multi-accelerator, in other words, there are many accelerator instances, but they have the same processing style. For heterogeneous data flow multi-accelerators, yes, there are many accelerator instances within the chip, but all the accelerators have different processing style, which is suited for different type of layers. And for workload, we used industry-inspired the real-time multimodal scenarios in AR, VR, and drone. And we evaluated these scheduling algorithms. And we had three variants of our scheduler. So which includes only the score-based optimization and smart frame drop and score-based optimization and frame drop and the super switching, which is the previous work from other group as one example of the operator level or layer level dynamic behavior. Then this is just a case study to show the our schedulers the capability to incorporate dynamic behaviors. And this is the overall evaluation results. So I'll not go over all the details in the interest of time, but basically what we observed is, on average, we observed 32% and 50% UX cost improvements compared to the two recent baselines. And I wanted to go over a little bit deep insight in this result to deliver the key insights. So this is the UX cost result for a 4KP system, 8KP system on the heterogeneous data flow accelerator. And y-axis, we have normalized UX cost, which is basically EDP-like metric for real-time multimodal workloads. And this is basically the evaluation study. So showing the impact of considering all the aspects of the workload characteristics and the smart frame drop and considering the dynamic behavior like supernet switching. The default one is the base dynamic scheduling with no adaptivity optimization. So we utilize the urgency score, energy score, like those basic scores, but we don't tune it for dynamic behavior. So the default one could be seen as our scheduler without dynamic city consideration. But as soon as you consider dynamic city by tuning the alpha and beta, we see this significant amount of the UX cost reduction, which shows the importance of considering the dynamic behaviors. And on average, we observe 32% the deadline violation energy improvements. And the supernet drop, the smart frame drop, and the supernet switching also helps, but the adaptivity parameter tuning was the most significant factor. And if we compare against the uh, only the static version, we can see significant reduction in the UX cost. So the implication of this is optimizing for dynamic behavior has significant impact on this type of workloads. So it's very important to consider the dynamic behaviors when we design a scheduler. So that was the learning from the scheduler design. And let me conclude this talk by summarizing everything. So I highlighted the emerging ML workload class, which we named as real-time MTMM or multitask and multimodal. Examples include AR, VR, and they have imposed unique characteristics leading to new challenges to ML system design, algorithms, scheduler, and so on. And real-time MTM and this new class of ML workloads requires new approaches to design ML systems in both hardware and software. And we need to thoroughly consider key characteristics of real-time MTM and workloads when we design ML systems. So those were the one sentence summary of all the learning from our recent research in the software, hardware, and this workloads. And if you're interested in the workloads, then we have the project homepage. So please refer to our project homepage. There are more resources regarding that. And thank you, everyone. And I'm happy to take any questions.
Thank you, Professor Kwon. So thank you so much for this very informative talk. And for the audience, if you have any questions, you can unmute yourself or you can input your questions in the chat box. I think maybe I can first to ask some questions. So, so I was wondering, so you have some kind of parameters. I remember for the uh dynamic scheduling score, that part.
Yeah.
Yeah. So I was wondering, so for that parameter is kind of the uh workload dependent or not? I know that it is kind of corresponding to a set of workload, right? But
Yeah.
like I'm not sure that is whether for the different sets of workload, the parameter need to be tuned kind of different kind of in a different way.
Yeah, exactly. So yeah, you mentioned the key aspect of this course. So yes, basically these parameters need to be tuned for each workload, and it is tuned during runtime. So
During
and
runtime.
yeah,
Okay.
during runtime. And one primary reason is because of the dynamic behavior, because the workload changes all the time because based on the dynamic behaviors, and we wanted to make it the scheduler adaptive to those changes. So these parameters are the for the adaptivity for those, and uh, as we found here, so we found that this converges very fast based on our algorithm. So it will provide quick adaptivity to workload changes under the dynamic behaviors.
So it's kind of online adaptive update.
Yes.
Okay, I see. Okay. And what is kind of the details of that the adapt of the update algorithm is like kind of like the generic algorithms or
It is more like it is kind of gradient descent inspired algorithm. So not
Mhm.
exactly gradient descent, but basically we when you run the workload on a system, so we modified alpha beta a little bit on the sampling point. So let's say the initial alpha and beta is 1 and 1 comma 1. Then we modified it to 0 comma 0.9 and 0.9. Then we run the system a little bit and we profile it basically for one frame or several frames. Move on to set the second sampling points such as alpha and beta equals to 1.1 and 1.1. We repeat that process and we measure the UX cost. Then we get over a sense how it looks like in the sampling points, and we just take best two and interpolate those values and move on to that point.
okay, I see. I
Yeah.
see. And another related question is that here for the energy
Yeah.
measurement, so there's some kind of I was wondering, is that kind of the hardware component like within the AR VR devices that can measure the energy, or because you
Oh,
need energy information to update the score, right?
right. Yes, yes. So we rely on the static energy estimation method, such as one integrated in the time loop or one integrated in the maestro. For accelerators, so the operations in accelerators is pretty much deterministic, and there are many cost models that provides energy estimation based on those characteristics. So we rely on those cost models.
Okay, I see. Okay, thank you. And any questions from the audience? You can input the questions in chat box if you want. So if not, maybe I can ask more questions because I have
Right.
a couple of questions there.
Yeah.
And and s- so first is kind of quite a general question. So I know you work a lot on those the AR VR workload on the systems level. So right now, from your vision, so right now, what is kind of the current bottleneck for the further broader deployment of those the VR AR, those are the visual computing, virtual computing?
I see, I see.
From the software side or from more kind of from the hardware side?
Yes, let me discuss it one by one. So basically, the major problem is we want to run too many models on the resource-constrained wearable device. That's the major problem.
Okay.
So many research problems come from that angle. So the model side, the people are trying to develop more lighter weighted models because of that, and try to align the model architecture more with the underlying hardware. And the hardware side, um, yeah, the heterogeneous one example. So the workload itself is quite heterogeneous. So how should they design the architecture? So that's also one thing. And recently the generative AI also is becoming quite challenging. So they have very different characteristics. And for generative language model, for example, there are this memory. The workloads are more memory bound. Then how should we address that in this small form factor? By the way, so people are also trying to run the generative language models on this kind of devices as well. So many works are going on, as you already might know. Um, so those are kind of emerging challenges, but basically the problem is coming from that we want to run too many things on the resource constrained devices.
So right now we're still kind of short of the sufficient computing power.
Yeah, everything, computing power, memory, and everything, bandwidth.
Okay.
Yeah.
Okay. And I think there's some questions in the chat box.
So I think we can go over one by one. So
Yeah.
what's the most important skill set a grad student should have to step into this field? Okay. Um, I, for PhD student specifically, I think you will get similar advice from many people, but I think you should decide your main field. So this area itself is very broad. So I covered ML workload, ML algorithm, and software and hardware, everything. But as a PhD, I think it may be a good strategy to focus on one aspect. So if you want to focus on architecture, then that could be a good field. Or if you want to focus on the OS runtime and scheduling, that's also a good field. So for PhD, I think focusing on the specific field, then you can also always increase your breadth after graduation as well. But this is just my thoughts. So please ask the same question to many people, so then you get better ideas. And the next question is in page 44. So let me go to 44. Okay, does the graph on the right side dynamic changes as system runs? And then yes, this changes dynamically, yes. And mainly because the workload itself is changing dynamically.
Okay.
Yeah, but the workload itself is not changing every frame, so it is not that extreme, but it will be stable for a certain moment and it will change eventually. So the parameter tuning itself is okay from that. But yeah, this basically changes over time.
Any other questions from the audience? Okay, and I promise this one last question from me. Yeah.
Otherwise, yeah.
So at the beginning of your slides, you mentioned that like the AR VR workload, and I also like the autonomous driving. So actually, so they have
Yeah.
kind of need kind of they have some much kind of similarity from the perspective computing, right? Right, lead the like yeah the slides, yeah, like the concurrent cascade model, real-time processing, those stuffs. So right now, because it's very interesting, you may know that for the autonomous driving, like the right now the new trend that from initialized from the Tesla is kind of the purely end-to-end model, right? So right now we don't need the multiple models for the perceptions, control
Yeah,
plan.
yeah,
We just have one big model, right?
yeah,
I think that from the perspective of the computing side, actually that can facilitate or simplify like the underlying architecture design or those stuffs. So I was wondering right now, so whether you predict that whether the development of AR VR computing will follow the similar trajectory that we use just a single like mega model and we have the multiple heads that can process the
mhm,
eye traction and the other speech recognition or stuffs.
yeah, yeah. Yeah, exactly. That's a very good point. So, overall, I think this is a matter of drawing the boundary. So, within the mega model, there's a backbone for processing the features. So, backbone could be seen as one model, and each head could be seen as individual models. And not all heads will be required all the time. So, I think we are getting to the similar aspects. So, yes, the workload itself is different, but overall, I think the problem still exists. So that's my high level idea. So
You mean such challenge will still be there, right?
yes, yes. So the backbone will be the upstream model. So every single head will be dependent on the result of the backbone. Sorry, excuse me. So yeah, and if we view the backbone and each head as a separate models, then we get pretty much similar problem, I think. So that's my overall thoughts.
Okay, I see. Okay. Okay. Thank you so much. And if there's no more further question from the audience, so let's thank our speaker again. Thank you so much, Professor Kwon. So give us this very wonderful talk. We really learn a lot. Yeah.
Thank
And
you for having me. I really enjoyed it.
yeah. Look forward to meeting with you in the person in the future.
Yeah,
Yeah.
me
And
too.
also thank everyone attending this talk this week. So see you next week. Okay. Okay. Thank you. Thank you, Professor Kwon. So
Thank you. Bye
have a
bye.
wonderful day. Bye.
Thank you too. Bye bye.